Swayam Prabha. Digital India. Educated India.
In the previous class, we saw the experiment called 2D head core, which was basically starting from hydrogen. You start from hydrogen magnetization, you evolve the hydrogen magnetization and you capture that as omega H T1. You transfer the polarization to carbon and detect the carbon polarization or magnetization, which is denoted as omega C T2. So, when you do a Fourier transform, you get the proton on the y axis and the carbon on the x axis. But we saw that that approach is not really the best approach. The reason for this is shown here. So, you see generally the NMR experiment, the sensitivity of NMR experiment is given like this. It is proportional, means there are other factors, but one of the factors is this, that it depends on what is the first nucleus that you excite. That means, remember we have been seeing all the while that we have been exciting protons with an RF pulse. So, the gamma of that nucleus matters, and what matters is the what nuclei is detected in the end. And in the proton experiment, both of these were hydrogens, but in the head core experiment this was hydrogen, but this was carbon, okay. And carbon is 4 times less compared to proton. So, obviously now you can see that if I have both, if I want to maximize my sensitivity, I should use both hydrogen as excited nucleus and also detect my hydrogen, not carbon. That would give me the maximum sensitivity possible. So, let us see for carbon how bad is the sensitivity if you detect carbon. So, this is what is shown here, that if I use proton as excitation, but detect carbon, there is a 4 times less. So, actually if you look at both carbon and proton excitation, so this is 1 by 4 if I use carbon, and this is 1 by 8 if I use carbon. So, if I start from carbon, I excite carbon and I detect carbon, then my sensitivity will be 32 times less compared to if I start from proton and end with proton. So, let us see again how this comes about. This is coming from this same equation. So, gamma of carbon is 1 by 4 of gamma of proton. So, 4 raised to 3 by 2 is basically 8, and 4 raised to, and the first one is 4. So, if I multiply these two, I get 32. So, what it means is that if I have both carbon as excitation and nucleus and detection also as carbon, my sensitivity is going to be 32 times less compared to hydrogen. Now, if I excite with proton but detect with carbon, which is we saw in head core, even then there will be a factor of 8, because this will be 1, that is excitation is 1 because I am using hydrogen, but if I detect carbon I will get 8 times less sensitive compared to what I would get if I also detect proton. So, therefore, as you can see, proton excitation and proton detection is always the preferred way to go about. Okay. Now, the question is, why is the sensitivity gain, how does it help us in real practical life? The reason is the following, that suppose I increase the time sensitivity by a factor x, where x is 32, I save a time by square of that. So, which is shown here. So, remember this is something which we saw in the earlier in the class in the first part of the course, where we looked at how sensitivity is determined in NMR, and we saw one of the factors was that sensitivity is proportional directly to the square root of time. So, if you do now, let us say that I have a sensitivity, let us say I have two experiments. So, let us say I have two experiments, experiment number 1. So, let us go back to this experiment number 1, which has a sensitivity, let us use the word sensitivity of 10, and I have experiment number 2, or I want the same experiment, I call it 1 prime, and I want a sensitivity of 20. So, what is this written here? So, what we are trying to see here is that I have an experiment number 1 which has, let us say, a sensitivity of 10. Remember, sensitivity is basically signal to noise. Okay. We will quantify, there are different ways to quantify sensitivity. In this course, we will always use signal to noise as a measure of sensitivity. So, if let us say my spectrum number 1 or experiment number 1 has a sensitivity of 10, that is the signal to noise is 10, and I want to improve the sensitivity and I want to get a signal to noise of 20. So, how do I do that? So, that means I need a factor of 2x, 2 times I have to increase the sensitivity. So, according to this rule which is shown here, that experiment is the sensitivity is proportional to square root of time. It means that I have to run this experiment 4 times longer, square. Okay. So, only if I run this experiment number 1 4 times longer, then it will become sensitivity equal to this 20. So, if I want to increase the sensitivity by x, I have to increase the time by x square. So, that is basically the philosophy in all NMR experiments in general, that the sensitivity to get a value you have to run experiment. Suppose you want to go from 2 to 4, that means if you want a factor of 2 gain in sensitivity, I need to run it 4 times longer. So, now if you come back to this here, if I need to get 32 times more sensitivity, remember carbon is 32 times less compared to proton. So, if I want to achieve the same sensitivity as proton, I need to improve my sensitivity by 32 times. That means I have to run the experiment 32 into 32 times longer if I want to achieve the same sensitivity for the same sample at the same magnetic field for a same signal to noise. So, 32 times longer is roughly 1000 times longer, 32 square times, sorry, square of 32 times I have to run longer, and that is 1000 times longer. So, which means that if I use a carbon and proton detection, and I use a carbon excitation and carbon detection, that sensitivity of that experiment is 1000 times or 32 times less, which means 1000 times more time is required. So, therefore, sensitivity plays a very important role in NMR because of this square factor. That means, if I want to increase sensitivity by a factor of x, I need x square more time to get that. So, that is why it is very important to minimize the time and increase the sensitivity, or if I increase sensitivity I reduce the time, vice versa. So, this is what is shown here, that to get the same sensitivity in an experiment where C13 is excited and detected, and if I want the same sensitivity as a proton 1D spectrum, I would need to record 1000 times longer. That is why carbon 1D NMR experiments are recorded for a longer time generally compared to protons. So, this is you will see typically in all spectrometers, that if you want to get a carbon 13 1D spectrum, we use much longer times because of this reason. Therefore, it is important to record everything in a short time. So, you see here this is a example that typically suppose I want to take carbon 13 spectrum, we usually record about 15-20 hours, whereas a 2D experiment may simply take 2 hours. So, this is what is trying to get in inverse detection. In a inverse detection approach, what we do is we directly go for a proton to proton excitation, means I start from proton and I end up also in proton. If I do that, then my time factor I can save a lot of time, because now the proton is the most sensitive nucleus. So, obviously starting from proton and detecting proton is the best approach. So, how do we do that? So, that approach is known as inverse detection when we go to 2D heteronuclear NMR. So, let us see how that can be implemented. That before going to that, you can see here the sensitivity which is we are talking about in terms of time has nothing to do with natural abundance. So, this is something which many times is being confused. People think that carbon 13 is less sensitive because of the gamma or because of natural abundance, one should keep in mind that both are important. So, if I take care of here, I am taking care of only the gamma part. That means I am improving the sensitivity only by looking at the gamma values. I am not taking care of the sensitivity which comes from the abundance. So, the abundance problem will still remain because carbon 13 is less abundance, but at least I have taken care by using the proton. This inverse detection takes care of only the gamma portion, that is improving sensitivity by exploiting the higher gyromagnetic ratio of proton. So, let us see how now a inverse detection experiment can be implemented or designed. This is shown here. So, we start from a hydrogen RF pulse or protons, which is the maximum sensitivity. So, we start from proton, we did apply a pulse on proton, but then instead of directly evolving as we saw here in the previous example, we immediately transfer whatever has come to the xy plane in this side here by polarization transfer to carbon. So, basically we directly transfer to carbon by using this inept approach. So, the inept approach, as I said, we will now denote it as a box here. We will see the exact sequence of pulses in the next few slides. So, once we transfer the polarization from proton, as soon as we apply the pulse to the carbon has come to the xy plane, and of course, it has not come, we apply a pulse for the carbon which is part of this block. Then carbon starts evolving because of the chemical shift, and that is what is denoted here, that during the period T1, because now the carbon is in the xy plane, the chemical shift of carbon is present here, and that is now captured as T1. But the sensitivity is higher now. Why is it higher? Because the polarization has come from hydrogen. Once the T1 evolution period is over after some time, remember we do not, as a picture denotes here, it is not that we wait till this gets over, it is that we stop somewhere in between. So, we have to, this is the standard principle of 2D, we evolve for some time and then transfer the polarization to the proton. So, what we are doing now, we are doing it, going it back to the proton. So, basically you can think of it like this, that a person has 1000 rupees and another person has 250 rupees. The person who has 1000 transfers the money to the less person having less money, and the person who has now less money becomes richer by 1000 rupees. He utilizes it for some purpose and then gives it back to the original person. So, this is like that. So, we are loaning the magnetic polarization to the carbon evolves with its magnetic chemical shift, then the loan is returned back to the proton, that polarization is transferred back to the proton again using the inept, but this we call it as reverse inept, which is just a reverse of this, okay. But this is also inept concept, but this is reverse, and then proton has now got back its polarization and it will now evolve with its chemical shift value. So, you can see here we are starting from proton and ending with proton. So, it is a proton to proton detection and excitation, but in between we have got carbon. Okay. So, we will see mathematically how now these two get connected. Now, one thing is when we finally detect the hydrogens, protons, now we have to decouple the carbon. This is the reverse of what we saw in the previous class. In the previous class we saw that we detect carbon, but we decouple protons. Here it is the inverse approach, that is why we use the word inverse detection. In the inverse approach, the proton is detected, but the carbon is decoupled. Again the same idea, why do you need to decouple proton from carbon? That is because protons are coupled to carbon, and therefore there will be a J splitting if I do not decouple, and therefore I need to record with decoupling the carbon. Now, if you go to this, let us see mathematically how what happens. So, we have a proton which is attached to carbon. So, we excite that proton, then we transfer the polarizations to carbon 13, and as shown here the carbon 13 evolves with its chemical shift value, which is now omega c into T1, and then we transfer this polarization back to proton like this, and what finally evolves is a chemical shift of proton in the direct dimension. This is called direct dimension. This is called indirect dimension. So, indirectly the chemical shift of this is captured in finally in the FID. So, now we have basically correlated the two chemical shift, because remember the final FID is a combination of this component and this term. So, basically we have two terms interconnected, intermodulated each other, and if you do a Fourier transform two dimensional, because I have two axes. So, now I will get omega c in the y axis, which is this omega c is because during T1, and omega this the 2 F2 dimension is now basically coming from proton. Okay. So, you see because of this factor here, the second dimension is omega h is because of during T2 omega h evolves, but any hydrogen which is connected to carbon, only those two hydrogen carbon like this shown here, only those carbon and hydrogen pairs which are connected to each other by J coupling, that is by bond, only those two proton and carbon pair will show a cross peak. So, that means this cross peak what we see in NMR spectrum in like this 2D inverse detection will be only those peaks where the protons are connected to carbon. So, if there is no proton attached to this carbon, example carbonyls, they will not be coming in this spectrum. So, in a 2D heteronuclear experiment, you cannot expect to see a carbonyl directly in a, unless there is a long range coupling, means suppose there is a hydrogen somewhere away from here and that is coupled to carbonyl, yes, then that may show up if there is a coupling. So, you basic requirement is that the hydrogen to carbon what we are transferring the polarization, these two should have an interaction between them through J coupling. Remember, we are not using the through space interaction here, but through bond interaction. So, they should be coupled by J coupling. So, this is the basic idea in any inverse detection experiment. So, let us see based on this what are the different types of experiment which we are going to see in this course and which are known. So, typically the words we use is HSQC, HMQC or HMBC. So, let us see that in this slide, in the next slide. So, here before we move on, an important point here to note is that you see what has happened here. If you look carefully at this terms, you see there are one is carbon and another is hydrogen. But if you recall, in the homonuclear case, we had proton and it was the same proton twice, because as I said last time, you cannot transfer complete polarization from one hydrogen to another hydrogen. So, therefore, most of it remains with its own, and that ends up as a diagonal peak. This is what we saw in the previous class, but in this case here in this type of experiments, you see what is happening is we have transferred the magnetization from proton to carbon. So, this using this inept. So, when we do that, inept has a 100% efficiency if I know the coupling value. Okay. So, typically I mean it is not exactly 100, one can never achieve 100%, but close to 100. So, let us say more than 90%. So, that efficiency can be achieved in an inept. Again, as I said, we are not going to go into the details of how that works, but that is possible to achieve almost close to 90% efficiency. So, therefore, nothing remains on carbon, everything, or nothing remains on proton, everything is transferred to carbon and everything is transferred back to proton. So, therefore, there is no proton evolution here. That means, this axis is always carbon and this axis is always proton. So, when these two are very different in frequency, remember proton frequency let us say is 100 megahertz, carbon is something else. So, there is no concept of diagonal here. Diagonal is only when the two frequencies are same in T1 and T2, but there is nothing like this here. There is a completely different frequency, completely different frequency. So, a 2D heteronuclear NMR spectrum does not contain diagonal peak, and this is a very important point which you should keep. But remember, in 3D we can get again a diagonal. So, whenever any two axes are proton, then you can expect to get a diagonal, but whenever there is a carbon proton or proton nitrogen or any proton X nucleus or any X and Y nucleus correlation, there is no concept of diagonal peak because the two nuclei are different. So, now let us go to this list of experiments that we will see in this course. We will look at basically 3 types of heteronuclear experiment. There are varieties of heteronuclear experiment in the literature in NMR in general, but we cannot go into all the 2D heteronuclear experiments in this course. Therefore, we will look at only the most important ones which are very routinely used in chemistry and biology for molecular structure analysis, and these are listed here. So, you see the acronym, they are acronym for HMQC stands for heteronuclear multiple quantum coherence, HSQC heteronuclear single quantum coherence, and HMBC is a slight variation, it is multiple bond coherence. So, what are the advantages, disadvantages of these experiments? So, we can go through this here. What is the comparison, where do we use what? So, as a thing written here, this is a one bond to proton to carbon correlation, which means that any two proton and carbon pair only if they are directly connected by only a single bond, okay, will be detected in this experiment, in this spectrum. Okay. So, we will not get any correlation, for example, from carbonyl, because in carbonyl there is no direct attachment of carbon to a hydrogen. So, only those carbons which are directly attached to a hydrogen will show a peak or a cross peak in this spectrum. Same is the case here. So, that is why it is HMQC and HSQC are very similar to each other in terms of the information. In fact, they give the same information. We will see that in a experimental spectrum down the line. So, this is one major difference, but if you look here, HMBC is a slightly different experiment. There you get correlation other way around, you do not get correlation if they are one bond. So, the idea is that one bond correlation is suppressed in HMBC because one bond information anyway comes from HSQC. So, there is no need to actually do an HSQC. So, we suppose I want to get information of a longer correlation, suppose I want to get carbonyl information, and carbonyl is not directly attached to a hydrogen. So, it is little bit away, there will be at least a 2 bond or 3 bond separation between a proton and a carbonyl, and that information, that is the protons which chemical shift which is correlated to a carbonyl is captured in this experiment. So, we basically look at a longer range coupling rather than a shorter range coupling. So, we will see this as we go along. So, that is the advantage of HMBC. So, the idea is the one bond anyway comes from this experiment. So, this experiment HMBC provides a little bit a longer correlation, a bigger, more information which is useful for structure. Now, compared to this, if the HSQC and HMQC are similar experiments, then why do we do one over the other? The reason is here that HSQC, as we will see, is a longer experiment, in the sense it does not mean it takes long time to record. What it means is that the whole experiment to execute in spectrometer, that is a pulse sequence, is longer compared to HMQC. So, therefore, HMQC is more sensitive and for in that respect, but it is less sensitive for some other purpose. We will see that later. So, HSQC is typically used for macromolecules, means biomolecules, and is very popular in protein NMR or in case of peptides. And HMQC on the other hand is ideal for small molecules, that is organic molecules, and that is what typically is done in the case of drug discovery or for solving structures of small organic compounds. Coming to HMBC, where is its use? Is useful again, as we saw here, it is similar in terms of assignment, it is useful, but it also helps to get the connectivity information which you do not get from these two experiments. So, as we saw here, it is more for a long range interaction information rather than short range. So, this is a very important popular experiment among spectroscopists and typically it is used in organic chemistry labs and pharmaceutical companies. So, let us start from looking at what is an HSQC experiment. This is what the pulse program will look like. So, this is a pulse sequence. So, what is pulse sequence means? If you recall, pulse sequence is the sequence of pulses which are applied in an experiment. okay, sequence of pulses and delays. It is not just the pulses, but the delays are also very important. So, these values are very specific values, and this whole scheme which is shown here together constitutes one experiment which we call it as HSQC. So, as we saw here, we will see more detail now as we go along. So, basically the is a inverse detection experiment, meaning we start from protons and do some things to protons and come back to proton in the end and detect the proton FID. So, let us see how that will look. So, this is the portion in circle which is denoted as inept. So, if you recall in the previous slides, we looked at what is an inept. We showed inept as a block or a box, more like a black box, but now here the actual scheme of inept is shown here. So, an inept, again remember we will not be going to detail, mathematical detail of how this works like a magic and achieves a transfer of polarization from proton to carbon. So, that part we will not be able to go in detail, but what it basically consists of a pulse, 90-degree pulse applied on hydrogen, then you give some delay, delay means a gap which is just a ideal delay period, and that value of that is given by this formula, and then you apply a 180-degree pulse on both of them. So, in this picture the broad pulses are 180 degrees and the short pulses are 90 degrees. So, remember what is the function of a 180-degree pulse in NMR? It helps to invert the magnetization. So, if you go from Z, it can take you to minus Z, or if you go from X, it can take you to minus X. So, that is called, when you take from a minus X to plus X or minus Y to plus Y, we call it refocusing pulse. When you take it from Z to minus Z, we use the word inversion pulse. So, you have to, this is just more of a technical jargon which one can keep, that an inversion pulse is just a 180-degree pulse, refocusing pulse is also a 180-degree pulse, but compared to the two, inversion is meant for Z magnetization to be taken to minus Z, but for refocusing it is going from minus X or Y to minus X plus X or Y. So, this is how we implement this whole inept, then you apply one more delay, then there is a magnetization, I mean a 90-degree pulse on both carbon and proton. So, typically in a 2D NMR pictures, if you read literature and papers, you will see like this, that we show the top portion as hydrogen and the bottom portion as carbon. And why is it shown like this? It is shown because this is hardware. If you go to the hardware details of this, when you apply a pulses, you apply on a proton channel. Okay. So, dedicated amplifiers, dedicated frequency generators and dedicated preamplifiers etc. are dedicated for protons, one set of them, and another set will be dedicated to carbon. So, when you apply a pulse on a proton channel, it is shown like this on the proton line, whereas when you apply the pulses on carbon channel, we will show it like this. So, this is typically the diagram. So, this is like a blueprint, it is a blueprint of the experiment which is conducted in a 2D experiment. So, for an expert, this is like all the information of the experiment is contained in this diagram. Of course, this is not a complete diagram on its own, details are omitted here which we are not going to go into, that is the phase cycling and the values of delays here and some more details, but overall this picture captures how this 2D NMR experiment is implemented. So, we will go in the next class into detail of this and see how we can analyze this 2D spectrum, how this mathematically the 2D chemical shifts are correlated in HSQC, look at some more examples of HSQC of simple molecules, and we will then look at HMQC.